Hello friends, welcome back to the tetrahedron chemistry classes. So guys, from today onwards I am also going to start that group theory part parallelly along with my coordination chemistry lectures which I have started, right? And in group theory part C, some part of this group theory I have already covered actually, the elements of symmetry which are essential to identify the point groups of the molecules, right? So I am giving the link in the description if you haven't seen that particular lecture of elements of symmetry, and also you are not having any idea about what they are actually, so you can go through that particular lecture to understand what they are. However, I will explain the things again and again, those symmetry elements and rest all other things again and again when I'll explain the molecules, right? If necessary, you can go through there actually, right? So in today's class, I am going to explain the symmetry element and operation along with the point groups of the molecules, right? So what is in symmetry operation, right? Symmetry operation is any kind of operation, right? Anything that is, you can see here, something done to to a molecule that leaves it in an equivalent configuration. Say for example, if you have any molecule and you are what you are doing, say you are rotating that particular molecule, and after rotation the molecule which you are getting, it is indistinguishable from the first one actually. That is called an symmetry operation. So symmetry operation, say you can rotate the molecule, right? Or you can reflect the molecule, or you can do rotation reflection to a molecule. Any operation you can perform which will lead to the new molecule which is indistinguishable from the original one is called the symmetry operation, right? Then after that there comes the symmetry elements which I have explained in detail in my previous lecture, as I have already mentioned, right? So symmetry element, you can see here, a geometrical entity with respect to which a operation is performed, right? So that geometrical entity could be anything. It could be a point, it could be a line, that is the axis, or say it could be a plane, right? So that symmetry element could be anything, right, about which the operation is performed. So how many types of the symmetry elements are there? You can see first is point, which I have already mentioned, that is center of inversion or center of symmetry, which is I. And second is, say, line. I have already told you line, that is a simple rotation or proper rotational axis, that is Cn, where n can have any number, right? Right. It can have your C2, C3, C4, C5, C6. Okay. And after that, you can see here complex rotation, improper rotations are also there. That is rotation reflection. First you will rotate the molecule and then you will reflect the molecule, right? And then you can have say planes, right? Any plane you can have, right? Any plane you can have, and like sigma planes, right? This is also sigma plane also, a symmetry element actually, right? So what is the principal axis of rotation? The axis with the largest n value. Say what is the meaning of that? If you are doing, say, a rotation of the molecule by 180 degree, right? So it is C2 axis. And if you are rotating the molecule by say C3 120 degrees, so it is a C3. If you are rotating the molecule by 90 degree, it's a C4. So if a molecule is having C3 C2 C3 C4, then the principal axis of rotation would be largest n value. That means among these C2 C3 and C4, your C4 would be the principal axis of rotation, right? And then you can have the horizontal planes. These are the sigma planes, right? And sigma plane actually it will bisect the molecule in the two identical halves. When this sigma plane is actually present perpendicular to the principal axis of rotation, right? Say for example, your C4 rotation is principal axis, and 90 degree to is 90 degree to this principal axis of rotation, you are having a sigma plane, that is called the horizontal plane, right? If in words you are not getting the things properly, right? So don't worry about that. I will explain all these things again and again. And then you can have the vertical planes. Vertical planes, again, they are also the sigma planes, but they actually contains the principal axis. That means they are parallel to the your principal axis, and this principal as the sigma planes contains the principal axis, right? And then you can have the dihedral plane, right? So dihedral planes means they are also the vertical planes, but these planes will bisect the angle between the C2 axis. For example, if in any molecule you are having the two C2 axis and the plane is actually bisecting the angle between these C2 axes, that is known as the dihedral plane. If your molecule is having all the planes, horizontal, vertical and dihedral, then priority would be given to the horizontal plane, and after horizontal plane the priority would go to the vertical plane, and last priority would go to the dihedral plane, right? These things I will explain again and again when I will explain the point groups. And now say what is the point group, which I have written here at the top, point group. So say in chemistry, see basically point group, actually the group theory comes from the mathematics actually. So generally what we done generally, we what we generally do, we actually apply the mathematical principles in the molecule, right, to get the information about the molecule. But in chemistry, if someone says what is the point group, so molecules are classified according to their symmetry elements. How many symmetry elements and what kind of symmetry elements are there are present in the molecule, which according to these symmetry elements we will classify the molecule. And you can see the collection of the symmetry elements present in the molecule forms actually a group. So say the molecule is having the C2 axis and a vertical plane, so C2V is a group actually, right? So this symmetry element will form a group, and this group is called a point group. Now why we call this group as the point group? Because we have to fix at least one position or one point in the molecule for the particular symmetry operation. Say for example, if I'm doing the C2 operation, then you have to fix an atom in that molecule, right? If you are applying say your sigma plane, then you have to fix a plane in the molecule, right? So that's why we are calling call this group as the point group. So steps, how these are the, see what kind of the steps, or what are the steps which must be taken to know the point group of the molecule. So first of all, you should know the exact shape of the molecule using hybridization and Vesper theory. So you can see, if you can apply hybridization, and with the hybridization you can get your geometry, right? Say for sp3 hybridization you are having tetrahedral, for sp2 you are having your trigonal planar, right? And after that you will also apply the Vesper theory, right? Say if your molecule is having the lone pair also along with your bond pair, then geometry would remain same but shape would change. This is very important to note that geometry and shape, they are the different things. Geometry is actually identified or decided with the help of the hybridization, and this shape is decided with the help of the Vesper theory. However, in a few minutes later, I will say the reverse of this. So kindly note that whatever I will say after few minutes, that is not correct. Correct is this particular statement, that means hybridization decides the geometry and Vesper theory decides the shape of the molecule. Once you know the shape of the molecule, then you can easily find the symmetry elements present in the molecule, right? And once you know the symmetry element, then you can make a collection or a group of those symmetry elements to know the point group, right? So what you can do, you can use the following chart. I can show you a chart, right? And by considering that chart or following that procedure, you can identify the point group present in the molecule. Or however, it is not mandatory to learn that particular chart. So it depends upon you actually. If you want to use that particular chart, then you will use that particular chart, or then you can otherwise you can go for the shortcut methods. Actually, shortcut methods are quite handy or quite useful when you go to the examination, right? So it depends on you whether you will use chart or you will use your shortcut methods to know the point group, right? So basically this is the chart actually, right? Symmetry point group. Say there are certain groups which have the very low symmetry, right? Like this C1 axis is there. C1 axis, you know, when you do the 360-degree rotation or to anything, right? Na? Then this will lead to the new molecule that would be the indistinguishable from the original. This C1 is actually the identity of the molecule, right? So if C1 is there, then CS is there, CI is there, then low symmetries are there. Then if low symmetries are groups of low symmetries are not there, certain high symmetry groups are there, then obviously if certain high symmetry groups are there, then the molecule would be tetrahedral, tetrahedron, sorry, octahedron, right? And your icosahedron, and then you can have your C infinity V and D infinity H. These groups can be present in the molecule. But if high symmetry is not there, and then you can have a common type of the molecules that is very frequently asked in the that are very frequently asked in the examination, right? So if Cn axis is there and this Cn axis is perpendicular to the C2 axis, if this happens, then the group would be D. If this not happens, then the group would belong to the C or the S, right? And again further you can do all the things actually. D is there, then D. If sigma plane is there along with the D, then the point group would be DNH. If sigma plane is not there but dihedral plane is there, then you can have D and D. If nothing is there, neither sigma, neither sigma H, neither nor sigma D, then it is only the DN group, right? And for your say C or S groups, you have this. If you have the sigma horizontal, then it would be CNH, right? And if sigma horizontal is not there, sigma vertical is there, then CNV. And if nothing is there, then you have S2N, and S2N is there, then that means S2N and then Cn, right? So it is not mandatory to follow this chart, right? However, in today's lecture I am not going to start from the first, right? I'll start from this CNV type of the point groups today, right? So it depends upon you whether you will use that particular flow chart or not, right? So guys, in today's lecture, I am covering this CNV point groups, and whenever you have the CNV point group, then you will have one Cn axis plus n sigma v. That means if you have the C2 axis, then you will have the two sigma vertical planes. If you have the C3 axis, then you will have the three vertical sigma planes. So the molecules which I will cover in this particular lecture, I will cover that water molecule which have the C2V say point group. Cyclohexane boat form, it is also having this C2V. Similarly, cis 1, 2 dichloroethylene, it is also having the C2V. 1, 1 dichloroethylene, it is also having the C2V. And ammonia is having C3V. Triflate ion CF3SO3 negative is having your C3V, and BRF5 with a square pyramidal structure is having actually the C4V. I will cover these molecules, right? And once I will complete the point groups part, then I will explain all the questions all related to this point group which have been asked in the CSIR net and the GATE previous year examination. Now we'll use see guys, it is very important to imagine the three-dimensional structure of the molecule. So whatever I have written here, so it is better, it would be always better you don't think about the H2O molecule, but you think about the shape of this molecule. Neither you don't go for the 2H and oxygen. You simply put a ball and then to another ball and then decide the geometry. This would be very useful for you, right? So now we'll take this, okay? So guys, I'm going to start this explanation on the point groups, and before starting the things actually, I have to, or I want to acknowledge this Symmetry Otterbin website. It's a very beautiful website and especially designed for the students as well as for the faculty members, so that they can teach, or they can explain the things little more detail to the students, so that they can have the better idea about the symmetry elements present in the molecule, which are very useful to identify the point groups of the molecule, right? So I have already told you, if you want to know the point groups of the molecule, then you have to have clear idea about the hybridization of the molecule. With the help of the hybridization, you can determine the shape, and by using the Vesper theory, then you can identify the number of lone pairs and the exact geometry of the molecule. Only then you will be able to identify the symmetry elements present in the molecule. After that, after with the help of these symmetry elements, then you will be able to identify the point groups of the molecule. So first I am starting with the say CNV type of the point group. You can see here CNV is written here where the cursor is right now, right? Cursor is here on the CnV point group. And first example, I am taking your water example. You can see this is your oxygen, and this is oxygen hydrogen bond. This is another oxygen hydrogen bond, and I have to identify the point group for this. If I know water is the V shape, water is having the V shaped structure. So first I am going to explain what kind of the Cn axis is present in the molecule. So I am clicking on this particular one. You can see it is my so what is written here, C2 axis. So how I can be sure that it is C2 axis? See, rotation of 180 degree around this C2 C axis. If exchange the two groups only, right, then it would be your C2 axis. It is a little trick. When the Cn operation actually exchanges the position of the two groups, then the Cn axis would be C2 axis. If Cn operation exchanging the position of three groups, then it would be C3 axis, and so on so forth, right? So here I am animating it. You can see here, this is your water molecule, right? So this water molecule after the C2 operation, you can see one more time here, right? 180-degree rotation. These two hydrogens are actually exchanging their position, and one thing you have to keep in mind, whenever we will do the 180-degree rotation to the molecule, that is C2 rotation, right? That means the groups which would be present on the which would be present below the plane, they would come above the plane, and the groups which are present on the above the plane, right, they will go below the plane after the C2 operation, right? So this is C2 axis which I have shown you, and then you can see your plane, right? So this you can consider as your XZ plane. So you have to keep in mind that Z plane is either above or below the plane, and X and Y you can consider anything. There is no problem in that. So you can see this is Z axis, XZ axis. I can consider this vertical as X, and which is going above and below it is Z. This is XZ plane, and in this XZ plane you can see this C2 axis and this sigma plane are parallel to each other. So this sigma plane is actually sigma V. Vertical plane is there, right? So one vertical plane and C2, then definitely the point group would be the C2V point group. So if you have only one sigma plane along with C2 axis, then it is C2V. If you have more than one vertical planes, then definitely it would be again C2V. So you have to identify only one, right? But to give you the better idea, I'm explaining another plane, right? This is YZ plane, right? So this axis is the Y axis, right? And Z axis actually above or below the plane. If I tilt the molecule in that manner, so you can very beautifully see this sigma plane is bisecting all the atoms present in the water molecule, two oxygen and two hydrogen, one oxygen, and the two bonds actually. But this C2 axis is also again parallel to, sorry, this sigma plane is again parallel to the C2 axis, so it's a vertical sigma plane. So the point group of water is the C2V. If I can show you all the symmetry elements present in it, right? So this is how you can understand, right? So these are the symmetry elements present in the molecule of water. I am not going to explain this actually identity. Identity is always there for any kind of the object or any kind of the molecule, right? Now we can see another example of this C2V, so that you can have the better idea about this one. So I have selected my second molecule, right? And my second molecule is actually cyclohexane boat, right? So this is your cyclohexane boat. You know cyclohexane exists in the chair form as well as in the boat form. So this is your boat form, right? And you can see this is my C2 axis which is going through the center of the boat, if I can show you in that manner. Okay, so this is going through the center actually. So I am converting into the boat, right? And if this is C2 axis, that means only two groups would exchange their positions, and the groups which will exchange their position, they are actually 180 degree at present, at 180 degree. You can see, you can focus on this particular group where the cursor is, right? And diagonally if you move, then you can see there this CH2 group is there. So these two are actually are at 180 degree angle. Similarly this particular one and this particular one, they are also at 180 degree angle, and similarly these two, right? So if I do the rotation, then this would exchange position with this one, this would exchange position with this one. Similarly, this would exchange position with this one. So I am going to animate this. So during this animation, you can very beautifully see. Fine, right? So again, one more time, focus on this one, and after rotation, you will see this will go there actually because they are 180-degree angle, are at 180-degree angle. So I am animating it. Right, so this is C2 axis. Now I can explain the planes present in it. So one plane is just like that, which is bisecting the boat, right, through their flagpole hydrogens and reflecting this CH2 CH2 unit and this CH2 CH2 unit. So this is your sigma plane, and this sigma plane is again parallel to your C2 axis. So the point group C, C2 and vertical, that means C2V point group. So you can see here at the down point group is the C2V point group, and you can see here this is one plane. So guys, don't confuse in this order and all these things. I'll explain all these things in the detail when I'll explain the group theory in the detail. Right now I am focusing on only on the point group, right? So this is one, and if I remove this XZ plane and putting next sigma plane, then you can find, okay, fine, one more plane is there which is bisecting the boat through the bonds actually this time, right? Through these horizontal bonds, right? And this plane is also parallel to the C2 axis, so it's a vertical plane. If I can show you all the symmetry elements, right? So this is how you can see your boat, right? Cyclohexane boat. Now moving to the next example. Now I have selected my next molecule, which is my say cis 1, 2 dichloroethane. So if I can put the molecule in the proper way, right, in that manner, okay. Okay, this is here cis 1, 2 dichloroethane. So these two green colors are chlorines, and green color balls are chlorines, and these small white are hydrogens, and this is carbon, carbon, and double bond, right? C2 axis is there, of course, right? C2 axis, and if I do the animation, then you will find just like that. You can see only two groups are exchanging their positions, two chlorines or the two hydrogens, right? So that means only two are exchanging. This indicates that the CN axis is actually the C2 axis, right? And if I can show you the plane, right, right. So this is the plane actually, right? This sigma plane is, again you can see it is parallel to this C2 axis, so it's a vertical plane, right? So vertical plane and C2 axis, so the molecule belongs to the C2V point group. And if I remove that particular sigma plane and show you another sigma plane, then you will find, okay, fine, this particular one, this is another sigma plane, okay, and this sigma plane is also bisecting the all the bonds and the atoms present in the molecule. You see it is bisecting two hydrogens, two chlorines, and the two carbons along with the bond, right? So if I can show you all the symmetry elements present in it, so I have to put one more sigma plane. So this is one more sigma plane. So this is cis 1, 2 dichloroethylene, which belongs to the C2V point group. Now very quickly for another molecule I can go here. So now I am selecting your 1,1 dichloroethane, right? So 1,1 dichloroethane means, if I can show you the molecule, wait a minute, okay. See what is here actually. Okay, fine, right? So you can see this is the carbon attached with the two chlorines on the same carbon. That means geminal chlorines are there. That means 1,1 dichloroethylene, right? And these are the two hydrogens. Very quickly I can show you the C2 axis present in it. Now this C2 axis is going through the molecular axis, right? So the rotation would be just like that. So this 180-degree rotation is actually converting. C2 axis means 180-degree rotation will give you the another molecule which would be indistinguishable from the original one. So this actually, right, they are actually exchanging, these two chlorines are exchanging their positions, similarly these two hydrogens. So this is the C2 axis. Now you can see the planes present in it, right? This is your again plane, right? If I put the plane in that manner, so this plane would see, you can, by putting this plane, these two would reflect and these two would reflect, right? So this will take this its position, and this will take its position, right? So I can animate it, you can see here, just in that manner. So they are reflecting each other, right? Say this is the reflection, not rotation. This is the reflection, right? So though both this C2 axis and planes are parallel, so again it is a vertical plane, and the point group is the C2V point group. But very quickly you can see the another plane present in it. If I can remove the first one, so this is your second plane, right? Second plane I can show you in that manner, okay, which I have already shown you previously with the different examples, right? So this plane is again going to the going parallel to the C2 axis. So this molecule again is having vertical planes, right? So C2V point group is there, and all the symmetry elements, if I can show you, I can show you these in that manner, okay? So this is your molecule, right? So these are the few examples of the C2V symmetry, right? And see in the text actually I have given you the more example. You can do the practice by drawing those structures on the paper and identifying the symmetry elements in the molecule, right? This practice you have to do, because without practice you will never understand how it is happening actually, because these molecules are very large in numbers. You may have any example in your examination, okay? So guys, now I am moving to the next type of the next type of the molecule. See, so far we have discussed the C2V. Now I am going to explain some examples or a few examples of the C2V. So I have written, though I have written lots of examples on the paper, I'll select only one or two molecules, right? To make you understand actually, right? So after that you can do your practice by yourself to know actually. So this molecule I have selected, this is ammonia, right? So this blue color is where nitrogen, and rest this is nitrogen hydrogen bonds first, this is nitrogen hydrogen bond second, and this is nitrogen hydrogen bond number third actually, and lone pair would be here actually, right, where the cursor is moving right now. So this pyramidal structure of ammonia is very important, right? Say if you have wrong impression about the ammonia molecule, just say if you put in that manner, so you may have confusion that this is actually a planar type of molecule, but it is not planar molecule. It's actually, see, if you view just molecule, then it will find in that, you will find in that manner, right? So three hydrogens are attached here. Obviously if I do any CN operation to it, if these three hydrogens are exchanging their position, 3 means that means it is having C3 axis, right? So this is how I can show you, right? So if I animate this particular one, okay, you can see here, this is the animation, right? So you can very beautifully see one at 120-degree rotation, clockwise anti-clockwise 180-degree, 120-degree rotation. These three are exchanging positions, right? You know 360 degree is the identity. If you divide 360 by 3, that will give you 120 degree. So 120 degree rotation means actually C3 axis is present. So one more time you can show, you can see here, right? This is the C3 axis, and see whenever you have the C3 axis or C4 axis more than actually C2 axis, then you will have the inverse action also, right? So this is C3 axis, and moving clockwise direction. If I can to show you the inverse, right? So if I take the C3 inverse, which I have written here, which the website is written here, if I animate this, you can see the clockwise rotation is there, but again the same thing, the three hydrogens are exchanging their position. So don't worry about the C3 inverse. If you want to know the point group, so you have to focus only on the C3 axis, right? So C3 axis is present in this molecule. Now I am going to explain the planes present in it, whether the planes are the vertical, horizontal, or your say diagonal plane. But one thing you will always keep in mind, whenever say three types of the planes are present in the molecule, vertical, horizontal and diagonal, then the priority would be given to the horizontal plane, right? This you have to keep in mind. So first plane I am going to show you in that manner, right? So this actually you can see here what it is doing actually. It is actually cutting the ammonia and this particular ammonia hydrogen bond, right? And by reflecting these two, right? These two. If I animate this particular one, then you will find this and this, they would exchange their position. How? You can see here, right? They are exchanging their position. That means sigma plane, right? And this sigma plane again, like C2V examples, this sigma plane is parallel to the C3 axis, so it's a vertical plane. So the C3 and a vertical plane, the point group of ammonia is the C3V. But this molecule is having more than one sigma plane. You can see one sigma plane in that manner. So you can insert another sigma plane, right? Which will cut this bond actually, right? You can see here, which will cut in that manner. The first sigma plane cutted this in this manner molecule, and see if I remove the first one, right? If I remove this first one, so your second plane is reflecting this and this hydrogen. Now if I remove the second one and putting third one actually, so cutting in that manner, so these two are actually reflecting. I can show you through the animation. So this is your animation, right? So this is the point group is the C3V, and to have the better idea, you can see all the sigma planes present in the molecule. So each sigma plane is actually cutting the nitrogen hydrogen bond. So that's why three nitrogen hydrogen bonds are there. So sigma planes are also three actually. So C3V point group for this ammonia molecule. Very beautiful example. Now we can move to the another example. Okay. Right, so this example I have taken, right, this is your triflate ion, right? This you can consider as the triflate ion. Triflate, you know, CF3, SO3 negative, right? So sulfur, you can consider this sulfur as yellow, and these are the three oxygens which are attached to this sulfur. And this is sulfur single bond carbon. This gray is the carbon, and these greens are the your say fluorines actually. So this is triflate ion, and it belongs to the C3V point group. So how C3V? So I can show you the C3 axis. So this is C3 axis, which is actually the molecular axis. So this is the molecular axis you can see, and this C3V axis passing through the molecular axis, right? So it's better to put the molecule in this staggered form, right? In that manner. Right, if I do this operation, what would happen? These three oxygen would would exchange their position, and similarly these three fluorines would also exchange their position when I rotate the molecule through this CN axis by 120 degrees. So this is the animation you can see. Right. So if you can focus here, this particular one, so this would come here, right, and this would go there. You can see one more time. Very nice, right? So this have come here and this have come here, right? Similarly, you can focus the rear your fluorines also. They are also exchanging their position. So I can tilt the molecule, right? Not only the oxygens, these are also exchanging their position, right? The green ones, right? So C3 axis is there, okay? And of course the inverse action would also be there, but I am not going to show you that inverse action, right? Now we can go through the planes actually. So how many planes? You can see this particular one. So this is the first plane actually, right? If I put the plane in that manner, right? So very beautifully what you are observing, if I can put the plane in that manner, just like that, okay. So these two hydrogens are reflected, these two oxygens are reflecting, and these two fluorines are reflecting. This is one plane. Now I am removing this particular plane, right? Now putting another plane. So this another plane would go through another bond actually, right? Just we have done for the ammonia, okay. These two are reflecting. If I animate this, then you will see, okay, these are reflecting ones, okay. Fine. Similarly, this molecule is having the third plane also, but due to the time constraint, I am not animating all this. You can go through the website and learn the things. So this is your second plane, which is bisecting in that manner. This is third plane, which is bisecting in this manner. So guys, the very important point, see C3 and V vertical planes are there. So the point group of this triflate ion is the C3V. So what you have noticed when you were doing for your C2V type of the point groups, then along with the C2 axis, two vertical planes were there. But whenever you will do for C3 axis, then definitely will have the three sigma planes, right? This trick you have to keep in mind. For C2V, one C2 axis and two sigma plane in general, and for C3V, one C3 axis and 3 sigma plane in journal. So these are the examples of the C3V. Rest you can do by right, guys. So I am taking one example of your C4V point group, and this molecule is actually your BRF5, right? So this is the interhalogen compounds formed between the bromine and the halogen, and you can consider in the center your bromine is there, which is red in color, and the greens are your halogens, that is the fluorine. And if you know the geometry by using the Vesper theory, then this molecule BRF5 is actually square pyramidal in shape, right? So you can see 1 2 3 4 are 4 CF bonds are in the square plane, and fifth is going above, right? So this is, if you connect all of them, then you will find the square pyramidal, right? So obviously you can see here, you now you can have idea that C4 axis is definitely here. How? You see, if you put the axis in that manner, right, where the cursor is moving right now, so and you do the 90-degree rotation, right? C4 axis means 90-degree rotation will give you the another molecule which would be indistinguishable from the original one. So four groups are there. Since four groups are there, then definitely it is a C4 axis, right? So I can show you, right? So this is your C4 axis, which is going through this actually plane. This is not plane actually, due to this your bromine fluorine bond, right, which is going above. And if I rotate, right, okay, so C4 axis, so the groups which are present at 90-degree, they will exchange their position. One more time you can see here, right, they will exchange their position. So if you see the geometry in that manner, right, you can see these two are at 90-degree, similarly these two are at 90-degree, and if I rotate the molecule in a better way, so these two are also at 90 degrees. So the groups actually, these two would exchange their position, these two would exchange their position if I do the animation or the rotation. So I am rotating one more time, you can check, right? So this is C4 axis, and whenever the C4 axis is there, definitely four vertical planes would be there actually, right? Or you can see, I can show you. So this is first plane, right? So this is first plane, which is actually parallel to this C4 axis. So it's a vertical plane, and it is reflecting these two with these two. See, if I can animate this one, you can see here, right? So they are actually reflecting each other. Okay. Then I can remove this particular one and put the plane in another manner. Then you will find, okay, one plane is just like that. If I rotate the molecule in that manner, sorry, yes, in that manner, okay. And if I do the animation for this one, just like that, you can see here. So it's a vertical plane. So I can show you the two vertical planes. So these are the two vertical planes which are present in the molecules, right? Then definitely there would be two another plane, but you can see there is no chance of another vertical plane. So definitely the planes would be there, but they will be they would not be actually your vertical planes, but some other type of the plane. But it is sufficient to know the point group. C4 axis along with the vertical sigma planes. So C4V is the point group for this molecule, but I can show you see diagonal planes also, right? Two planes I'll again show you. So this is the diagonal plane, right? So what is the meaning of the diagonal plane? You can see here. See, it will actually go through this particular C4 axis. If I you can see here, and this will also cut the molecule in that manner, right? So it's a diagonal plane. However, I'm not going to explain the diagonal plane in pretty much detail, though, because I have explained this on the paper actually, right? So due to the time constraint, I'm not going into the detail, but you can see that this diagonal plane is also vertical, is parallel to this C4 axis, so it's a vertical plane. See, one you can have this one, and then you can have the second diagonal plane, right? So diagonal plane is actually what it will do. It will actually bisects the sigma plane as well as your say C4 axis, right? So then you can have another sigma plane. You can see now this is the sigma plane, right? So this diagonal plane is actually bisecting the sigma plane vertical as well as the C4 axis. So second, in that manner you can see, right? So these are the vertical sigma planes, these are the diagonal which are cutting the bonds, or right, bonds also. So this is the example of the C4V point group, and the molecule is BRF5.